All right, we're back. We are Game 2005 in the fall 2019 semester at George Brown, and it's Lesson 7, Part 2. We're going to talk about kinematics again, covering some of the physics stuff that we missed, and motion in 2 dimensions this time. We talked about motion in 1 dimensions, and we also did a bit of programming the last time. But this time around, we're going to talk about the concepts behind the programming that we did last day. So let's start with that today. There could be a couple of videos around this. This is the first in a series. Again, Lesson 7, Part 2. So we got together to talk about things like other new definitions, speed, and so on. What speed is, what velocity is. We talked about those kinds of things, those concepts. What acceleration is, and usually everything that we learned in calculus we're starting to use now. We're starting to relate position to acceleration and velocity. We're starting to look at all those relationships, and in this particular case, gravity and its direction pulling downwards is something that we're going to be using. When it comes to 2 dimensions, we have this idea of a component-based system where we have, that's why vectors are good, where we're going to use a component in the x-axis as an example this way, and we have a component in the y-axis this way. You can see there's 2 components here, whereas in 1D motion that we talked about a couple of lessons ago was only across 1 axis. So you can see what's happening here. We have acceleration happening across the y-axis. So you see accelerating, it's getting the time between the motions, they're getting longer and longer, or each frame, the object is moving farther and farther out. And you can see at the same time, though, something funny is happening on the x-axis. On the x-axis, it's consistent. The time is not growing. There's no acceleration here on the x-axis. It's going the exact same rate from one moment to the next. So this is kind of a motion to describe, again, a particle moving in 2 dimensions. So we can describe this like we talked about in class. When it comes to this with vectors. Okay, so we have our final position, and usually you can look at this as range or displacement. Our final position, and again, this is a way of looking at vectors, minus our initial position is our change in position, our total displacement, if you will. And you can look at that as 2 different vectors here. So we've got a vector, so this is the, again, initial position, and we've got our final position, and we've got a vector which is the change in position from one location to the other, from time initial to time final. This graph describes that motion, again on the x and y plane. So the idea when it comes to this is we can extend these type of equations to, again, multiple dimensions. Usually we can go from 2 to 3 dimensions, no problem. And as you can see here, when it comes to the average velocity, the way we would calculate that then is to look at, remember, velocity's displacement over the change in displacement over the change in time, and that's what this describes here. You have the displacement, change in displacement vector over change in the time scalar, and then that gives you the average velocity. So we talked again. This is just review of what we talked about in class. And we're going to skip over this a little bit, but basically what this is when we want to find the instantaneous velocity, what we're really going to do is use calculus, right? All the work we've been doing in calculus up at this point is to help us find the instantaneous velocity or the instantaneous acceleration, based on the original position curve, on whatever that is, right? So if I want to look at a position at 2 time frames and say, okay, so here's where I was initially, and this is where I'm going to be, kind of in the final, this other time frame. How fast, or what's the velocity vector when it relates to this? How can I find the instantaneous velocity at that particular moment? And you can do that by using calculus. So we're going to skip over these. When we want to find the average acceleration, then we can do the same thing that we did with the average velocity. The average acceleration, we can look at it with respect to ranges. We look at the average, the change in velocity over the change in time, and of course you can break this out into final velocity minus the initial velocity over the final time minus the initial time frame, And a lot of times what we'll do is we'll take this idea and expand it to this form, which we can later use to create other other algebraic magic to solve some kind of problems for us as we go forward, as you'll see. So again, as the particle moves, you can see that the particle is moving as a vector, right? Here you can see that the initial range or initial displacement, and here's the final displacement. We have the total displacement here, but this really talks about the average acceleration being, a change in velocity. So here's our velocity vector here. You can see the velocity vector changes. It goes in a different direction. Although when you look at this particular graph, it looks very similar in terms of magnitude. We're going to get a change in direction here. And again, instantaneous acceleration we're going to figure out by using calculus, just like we've talked about before. I'm not going to go into this right now. So again, magnitude and direction. We talk about vectors, and we want to use vector or linear algebra, vector math, to describe the motion that we're going to be seeing. Once we start getting things in 2 dimensions, and when we have constant acceleration, and we can start using our kinematic equations. Okay, so again, let's take a look at these kinematic equations that we start off with. A lot of them are going to look very similar to the 1D kinematic equations that we talked about a few weeks ago, right? So again, here we can say that our range is equal to, again, all the components on the x-axis initial plus the y-axis initial. That's what we're looking at. The components on the x-axis plus the components on the y-axis gives us the total, the position that we're looking at here. Once we know this idea, and these little hats mean component kind of thing, we can see that from a velocity perspective, we have a change in the location or change in position over the change in time, right? We can break that down to saying that we can take our velocity and the component on the x-axis multiplied, or velocity times the component on the x-axis plus our velocity on the y-axis, and that's what's going to equal this total velocity. Knowing that, then, when we reform this equation, we can look at the final velocity then would be equal to the initial velocity plus AT. And this looks very similar to one of the equations that we saw a couple of weeks ago. But again, keep in mind that this velocity is on both axes, x and y. And of course, this is very similar. We actually coded this one last time. We used the final position, that's what this is, a final displacement, if you will, is equal to the initial displacement plus the initial velocity. This is again both on the x and y axis, times time plus 1/2 AT squared. This kinematic equation gives us the a graph that allows us to map the particle's trajectory, if you will, over time. And you can see what this looks like when we look at this. From this perspective, we can say that here's my velocity initial, plus we have my acceleration, for a certain amount of time. We can see that that velocity is going to be a different velocity. The velocity final obviously is going to be influenced by both the initial velocity vector plus the acceleration vector times time, and that's going to give us this new velocity vector in a new direction. Furthermore, if we take a look at the next one, we can see that our final position then is taking all those terms. So again, initial position, initial vector. Here's our initial vector or displacement vector, plus the initial velocity vector times time, plus 1/2 of AT squared, that particular vector, and we can see that's going to give us our final position. Knowing that these can all work together like this, and we can use vector addition to get there, you can see each term can be broken down into its vector components. And that's how they're related. So when it comes to projectile motion, everything that we're going to be looking at in terms of, this semester it's all going to be particles. Everything is a particle. Everything is a projectile, right? So we're looking at projectile motion here. So think about this as, when it comes to a projectile, something that's going to be emitted or driven as an example, we're going to take a particular mass and we're going to, kind of push it into a particular direction. So again, across both axes, the x and y axis in this case, we're going to have forces across the x-axis, or energies across the x-axis, and energies across the y-axis. They're going to occur simultaneously, and normally, because a projectile is in gravity, you're going to see a curve kind of that looks like this. So again, we have to make some assumptions around projectile motion. One, we're not going to use any kind of friction, right? Second thing is, it's going to follow a parabolic path, and this path is usually called a trajectory. We talked about this. And again, here you can see all the energies for each of the final vectors broken out into their component piece parts. So you can see that this is the y-axis component times the velocity, and this is the x-axis component times the velocity, and you can see that you're going to get a nice parabolic arc. So there's different kinds of motion, and this is the first common type of motion. And this is where, for example, you are on a horizontal cliff or some kind of elevation, and what you're going to do is you're going to fire your projectile, but you're going to, almost like you're dropping it off the cliff. That's what you're doing here. So yes, you could have an initial velocity, but most of the time there's no velocity. It's just like you literally are dropping it off a cliff. This goes with Galileo's equations that we saw again a few weeks ago, when he basically talked about this idea of, dropping an object off a cliff. Or there's three motions. To remind you, you can drop something, drop a rock, you can toss a rock up in the air, right, as an example, or you can throw a rock down. Those are the three types of motions. Here, this is the first type of projectile motion. Again, it's using kinematics, but we're doing it in 2 dimensions. And you can see here that the first equation we're going to look at is the change in displacement across the y-axis is equal to the initial velocity times time plus 1/2 at squared. And again, we used something almost very similar in our equations when we built our C++, kind of solution. Across the x-axis, you can see that the change in displacement across the x-axis is just the velocity on the x-axis times time. Okay, so that is more consistent. It doesn't grow like the acceleration one does here. Notice that there is no acceleration component across the x-axis in this case. So you can use both of these equations to determine different kinds of numbers or solve certain problems. For example, how long does it take for an object that is being propelled off of a cliff to fall a certain height? And what is the range? What is the separation from the edge of the cliff? How far will it travel, before it hits the ground, given a particular velocity, as an example? And we have some examples of this. We have, if I want to find the velocity, as an example, the total velocity is going to equal to the square root of the velocity across the x-axis squared plus the velocity across the y-axis squared. And you can see that this looks very familiar. In fact, it looks like the Pythagorean theorem. So again, c squared is equal to a squared plus b squared, or c is equal to the square root of a squared plus b squared. This looks very similar to that. And that is in fact what's happening. You're going to use a triangle to describe the motion that we're getting. We can also look at it like this, where we have your final velocity on the y-axis is equal to your initial velocity on the y-axis plus at. And again, this is just on the y-axis. This could determine, example, if I knew some information, and remember, we always know that the gravity or gravitational acceleration is always going to be negative 9.8 meters per second squared on the y-axis. So if you were to fill some of this information out, you could isolate t. How long does it take, given that your initial velocity across the y-axis was whatever, right? And if you were to find this out, if I said, let's say, for example, I want to find the final velocity. Given that my initial velocity was 0 on the y-axis, I'm dropping a rock, right? Plus at, where a is just, gravitational acceleration. How long will it take? What's the final velocity given this many seconds? Whatever that many seconds is. Sometimes we need other equations too, but you can see that this is exactly what's happening here, right? You have an initial velocity on the x-axis, 20 meters per second. So, for example, let's say in this particular problem, you have a cannon on top of a cliff. First type of projectile motion. You know, projectile is fired. The muzzle velocity is 20 meters per second. You notice it's going to stay. The length of the vector, the velocity vector across the x-axis, stays the same size consistently. It keeps staying the same size, until it hits the ground, right? However, the velocity vector across the y-axis continues to grow, right? This change in size of magnitude is easily seen as an incrementing or increasing velocity due to the acceleration of gravity, gravitational acceleration. And you can see that the number is a negative number because we're going in the negative direction, downward, right? Now again, when we saw last week when we were doing our video on C++, down the screen is usually a positive direction for computers because usually the top left corner is where the 0, 0 point is. Here we're using, you know, Cartesian coordinates, so we're looking at 0, 0 is the bottom left corner, or the origin is the bottom left corner over here, and so this would be, you know, a negative motion. A lot of times what we want to do when we try solving our problems is, you know, break it down between horizontal and vertical. We want to take those components and break it up, and a lot of times it helps us solve our problem, right? So again, if we think about this, it says consider a ball falling off a table. What should the equations of motion be? Which ones would we use if we had a ball falling off a table? And again, my question would be, what is the initial velocity? So if I go back to this, I would go back to these two equations first. So, cool, what's the height of the table, as an example? Okay, what's the initial velocity across the y-axis? Well, if I'm not throwing it down, and if it's just falling, then this would be 0, this first term, right? Cool, okay, so we know what the distance is, the displacement, positive displacement of the table. This would be a positive number, as an example. And then, again, actually, one thing I should note also is where you draw your axis is very important. You could draw an axis for this particular graph here right at the corner. So here's this little particle or projectile, and we could draw an axis right through here, right where the ground plane is, right here on top of the cliff. Or you could elect to draw the ground plane down here. Either way, whatever you decide to do, you'd have to adjust these values that you put in here. So for example, if we know that this is going to travel downwards, and this is the negative height, because we're going to go down into the ground, because if our ground plane is up here, you'd put a negative value in here. Negative value, and then you would say that it's with a velocity, initial velocity times time, plus 1/2 of AT squared, where A is gravitational acceleration, would be a negative. And then when we're solving for time, we would take a negative divided by a negative, and we'd get a positive. It's quite simple. So in this case, it makes sense to have a negative amount that you'll be traveling down based on the height of the cliff. And we'll see this in a second. So here we have an actual example. So let's try and figure this out together. So the first thing is a ball rolls off a table with a speed of 3.2 meters per second. The table is 1.5 meters high. We know some of these things. When does the ball hit the ground? That's the first question. And how far away from the edge of the table is the ball when it reaches the ground? And then, finally, with what speed does the ball hit the floor? So there's 3 things we need to answer. So how do we break this problem down? Well, first I would look at both horizontal components, x-axis, and vertical components, y-axis, right? So going back up, if we go back to the initial equations, we could start writing some of this stuff down. Okay, so again, I would probably take this equation first. All right, here we go. This is equation number 1, and try and fill in the blanks. So can we fill in the blanks for equation number 1? Does this make sense? So okay, if I take, the initial equation here, and I start plugging in some values, so it rolls off a table with a speed of 3.2. Is that this? No, this is on the y-axis. So this would not be the initial velocity. Initial velocity here would be 0. We're going to come back to this in a second. However, we do have this other equation here, which I'm going to use. And really, when we think about it, what we're really saying here is the displacement across the x-axis is equal to the velocity times time. We know that the initial velocity here is 3.2 meters per second. Let's try and fill this information in. Can't fill it all in right now. We're going to start filling some of it in. So we know that this part is 3.2. We don't know what the time value is. We don't know what the displacement is. We don't have that information. In order for us to find the displacement, we need time, and we're going to get time by this, because remember, just like we saw before, just if we were to drop a rock when it comes to projectile motion, I'm just going to go all the way to the top of here. You can see that we know how long it takes for an object to hit the ground. By the way, this amount of time is the same, doesn't matter what the mass is, right? So knowing that, we can find the time value. We can plug into that part, but we need to get the time value first. So going back to this, so yes, this is nice. This is how we're going to do it. Here is what we need to do. So let's plug in some values that we know. Again, just going back to this. I know that the total displacement on the y-axis, if we assume that the coordinate frame starts right here at the top of the table, right? We know that this would be a negative 1.5 meters. That's how far it would travel. So again, because we're traveling in the downward direction. So let's do that. So we're going to say that this is negative 1.5 meters per second, right? We know that. We know that the initial velocity across the y-axis only would be 0. So that would be 0 and then times time. We don't know what time is, but anything times 0 is just 0. And then 1/2 AT squared, where A is equal to the force of gravity. Force of gravity pulling in the negative direction. So that would be like negative G, or negative 9.8 times time. So we know these things. And then let's continue carrying this forward. We could simplify this by removing this part, because there would be no need for that. This second term would resolve as 0, because 0 times t is just 0. This 1/2 times negative 9.8 would be negative 4.9. So let's just do that. It's negative 4.9. So we have something that looks like this right now. And what we want to do is we want to take this and rearrange it so that we're isolating for t, right? So t squared would be equal to some value over some other value. So let's copy that. And we can see this as something that looks a little different than this. So I'm going to see if I can pull in the formula, insert. Again, we're going to go for the equation, and we're going to go this y over x form, y over x. And what we want to do here is we want to say that this is negative 1.5. Just rearranging this right now, bear with me, over a negative 4.9. Negative over a negative, we would instantly know is a positive number, so we're just going to keep that as a positive number, and that works for us because guess what? We can't have negative time values, right? So this would be totally cool. Let's erase this. I'll make this equal to t squared. There's t squared. So t squared is equal to this. Rearranging this, and I'm just going to move these up so we can have more space here. And I'm going to, kind of zoom in just a little bit so we can see what's happening. Rearranging this and just moving it up. If I was going to rearrange this one, I would say that let's put t on the other side. So we'll say that t squared is equal to 1.5. So just rearranging that so it looks what it's supposed to look like. There we go. And what I want to do now is I want to solve for t. So again, we would just put this in the square root. So I'm just going to put that next to it over here. So we can say that t then t then is equal to the square root of this. Let's just install the square root there. So again, insert, and we're going to go to equation, and we're insert the square root like this. And here is where we want to take this and put it in there. And so we have something that looks like this now. Well, if we use our trusty calculator, we can find out what 1.5 is over 4.9. So we calc 1.5 divided by 4.9, and that's equal to this value, 3.06122 something or another. So again, if I was going to take this further, I'm just going to put it next to it just to save room. Normally you wouldn't. You'd put it underneath it. But we would say that this part right here would be equal to, again, 0.3061. Let's just take it to 4 decimal places. 0.3061. I'll leave this here for our calculations though. 0.3061. Right, and whatever else. And t then would be equal to the square root of this. That's how much time it's going to take. If we take the square root of this, and going back to this part, the square root, we can see that time would be 0.5533, rounding to 4 decimal places. So t then equal to 0.5533 seconds, right? Okay, that is our time value. We figured out our time value. There it is, right? We solved for time. That's how long it takes the ball to fall off the table. Now that we know this, we can find the total range, right? By taking this same time value, multiplying it by 3.2, which is the initial muzzle velocity, or the initial velocity that the ball rolled off the table. We can plug that value in. So let's move this around. We can say that delta x, the change in x, is equal to 3.2 times 0.5533 seconds. Right? So once we've done this, we can multiply this by 3.2. Luckily, we still have this thing up here, so multiply by 3.2. And you can see now that it is equal to 1.7705. 1.7705. So again, taking this, we know that because 3.2 is meters, we know that this is 1.7705 meters. That's the total change in the x direction. That is answering this question. So when does the ball hit the ground? The first question, that is 0.5533 seconds. How far away from the edge of the table is the ball when it hits the ground? Well, that is just 1.7705 meters. Okay, now the next one is with what speed does the ball hit the ground? Okay, that is a velocity question. So now we can look at other equations to help us with that one. So let's take a look at that. Again, using the same PowerPoint, we know for situation number 1, or for projectile motion of the first type, we can see that there are several equations here. So we know the distance, we know the time, and we want to find this out. So what is, if my initial velocity across the y-axis is 0, we want to find, we know what the time is, and we know the acceleration, we can find the final velocity. So this is the equation we should use. So again, going back, I want to find the final velocity. This is the last one. I'll put this one down here. I'm just going to make this a little bit smaller for us, and we'll plug that equation back down in here. Right, so we know we want to find this third, so this is like question 1, question 2, and here's question 3. So we have all this information, right? So what is a t? Well, we know t, right, is equal to 0.5533 seconds. We know that. We know a is just gravity. So this is going to be a negative number, right? So negative 9.8. And we know the initial velocity on the y-axis is just 0. So we can plug that number in there too. So this is 0. So then we're left with this, right? This is the equation here. So let's bring these up. And so when you use that calculation, we just want to make that calculation happen. Negative 9 times 0.5533. So again, 0.5533 times 9.8 negative plus minus, again minus 5.4223 roughly, minus 5.4223 meters per second. So again, I'm just going to take this whole thing, go back to here and just plug it in right here. This is meters per second. Okay, so now we've answered all three questions. So hopefully you saw that. So again, we started off by using the component equations for both the horizontal and vertical axis. Given the information that's been provided to us, 3.2 meters per second and a table height of 1.5 meters, we set the axis at the top of the table, and then we started plugging in, the different information. The one tricky part might have been this, which is 1.5. This would be normally 1.5 meters, and you see this is a height. Now this could be seen as different if the initial height was a positive number. If we, for example, started our axis down here, we can see that this would be 1.5 meters instead of negative, right? If we did that, then the thing is, we would start off with a different position. So our total y would start we would treat this whole thing a lot differently than we're doing because of where we're putting our axis. We actually translate everything that we're doing here. One thing we couldn't do is use a negative 9.8 anymore, because once we did a negative 9.8, then t would be negative, and time, unless you're a time traveler, can't be negative for our little examples. So this wouldn't work out, and that would be a good indicator that we've done something wrong. We've looked at this model in the wrong way. All right, let's get to the next type of motion. So second type of motion is a little bit more complex in some ways. We have two things. We have something called the kicking angle, or the angle of incidence, if you will. And we also have the initial velocity. Notice these things, the angle is in radians, normally on a computer. Here we're dealing with it in degrees. And this kicking angle is a positive angle from the horizontal, from the plane that you're looking at. So this is where you can see this little man. He's being kicked off, kind of shot out of a cannon at a particular angle. So that's the motion. It looks very symmetrical. And you can see now that what we want to do is we want to break up this velocity. We haven't been given the other information we had before, right? We've just been given velocity and an angle. So that's normally what we've been given here. Velocity and an angle, and then once we get those two things, we want to find out, can I break out the velocity, the initial muzzle velocity times a particular angle, can I break that down into its component piece parts? And one thing that we talked about in class was that normally when we talk about this kind of problem, we relate cosine to x on the x-axis and sine on the y-axis, because that's what we normally do. However, this is not always the case, and we saw that in last week's lecture on Newtonian physics. We started talking about different things. So you can see here that here's the initial velocity, here's the angle, and it's going to follow this parabolic path or trajectory. So now we have some additional information. If I know the velocity on the x-axis and the y-axis, and I want to find the time, as an example, if I only want to know the time, right? So I want to go from the time it takes from A to C is 2 times 9. Typically time then, if we're looking at equation number 8, equation number 8 is kind of a repeat of what we've already seen. Final, velocity is equal to the initial velocity plus AT, that's us dropping something. Even a cannon, that's the y component. And then we can extend this idea. If we bring, things over to the other side, we can take this initial velocity across the y-axis and break it down into the initial velocity times sine theta. So this is, we know that the final velocity on the y-axis is going to be 0 because it's going to hit the ground. When it hits the ground, the velocity is going to be 0. Finally, it's going to stop, right? And we know that A is just gt. When we rearrange the equation, we solve for t. We can find out the t, the time it takes, right, for us to go from the bottom to the top of the arc. This means from A to B, right? would be when the velocity becomes 0, that's when it hangs in the air. That's the symmetrical motion that we've seen before, right? So velocity there is equalized. It comes into equilibrium with the acceleration, the downward acceleration. The upward velocity becomes kind of canceled out, and we have 0 velocity there. And so once we know that information, we can substitute some values that we have here. So once we know that this is the time that it takes to get to the top, we know the motion being symmetrical from here to here is equal to the motion from here to here, given that all things being equal, wind speed and velocity and all that kind of stuff, air resistance and so on. So if we know that, then we can just say that, well, the total time it takes from A to C is just 2 times that. So whatever this is, multiplied by 2, and that's the total time. All right. Furthermore, if you want to know the total height, so these are some equations to find things like, okay, what's the total apex that this is going to travel in? Well, the way we can figure this out is we start with equation number 11. We know that, going back to Pythagoras, c squared is equal to a squared plus b squared. We know that, right? We also know that the final velocity squared is equal to the initial velocity squared plus some kind of 2 times the acceleration across the y-axis plus the total distance across the y-axis, whatever that is, right? When we move things around and we break things out, we know that the final velocity, again, is going to be 0. That's the velocity at the apex, where Vy is 0, right? We know then that we can break out this equation here, y initial squared. We can break that down into v times sine theta, where we're relating sine with the y-axis, all squared, plus 2, again we're multiplying times 2, g, which would take the place of ay, acceleration across the y-axis, h, which is the total height, the total displacement. Solving for h, we get h is equal to v squared sine theta squared, so sine theta all squared, that's what that is, divided by 2g. And that is your equation for height. That's how we get the height equation. Alright, so how about the range? How do we find that out? Well, we know that it's going to be very similar to what we've seen before. The total range, still, it's going to be a consistent number. And again, going back up to that initial slide that we saw the projectile, way up here. Let's go back up to the top here. And let me just view normal for a second, just so you can help me visualize where we are. Yeah, this one. So you can see that, remember, on the x-axis, it's exactly the same. Every single frame, every step, every second, depending on whatever your time frame is, it's the exact same. That distance isn't going to change. And so going back to what we had then, you know, as an example, we know that this velocity on the x-axis times t is going to be remaining pretty constant, right? However, we want to break out this component, and to get the velocity across the x-axis, we take the initial velocity, whatever that is off the cannon, times the cos of the angle, and we multiply that by t, so this is the range. Okay? So that is the total range, you know, that we're going to go from, you know, from one part to the other until the object hits the ground, right? We already know that range is, if range is this, right? If we know this, and we know that from A to C, it's 2v sine theta over g, and we know this because of going back up to this, 2v sine theta over g, that's time. You know that this is true. Time is equal to 2v sine theta over g. That's equation number 10. That's why it's brought back in. That's this. That's t. And notice that's what we did. We took r, which is v cos theta t, and we broke it down into its component piece parts. This part remains the same. That's this part. And we replace t with 2v sine theta over g. Multiplying this out and solving for r, we can simplify down to v squared sine 2 theta over g, and that would be the total range that we would travel based on the initial kicking angle on the upwards direction. Okay, so those are the values that we have to work with when it comes to solving parabolic paths or projectile motion of the second type. Then there's the third type of motion. And the third type of motion is kind of like the first two motions componentized and put together. So you can see here that we've got an initial velocity at an initial angle from the horizontal on the top of the cliff. And you can see that this motion here is going to follow a natural and symmetrical parabolic arc to, let's say, somewhere around here. And if that's the case, then we also have something else where we can kind of guesstimate how long it's going to take. First of all, we know that what comes up must go down. So the initial velocity upwards is going to be equal to the initial velocity downwards. That's by Galileo. And now we can actually start monitoring from here all the way down. That's one option. The other one option is, what about if I took it to the point where the projectile was at zero velocity across the y-axis? That's like equivalent of taking an object to the top of its apex and dropping it off a cliff, right? That's what this is saying. So we could break it down like this. Take this object, move to the top of the apex, and then from here split it down the middle and then let it drop. You know, given that it's traveled a certain height, you know, height capital H. And then it would just travel all the way down to the ground. We can break this thing down. But there are specific equations to help us with this as well, right? And for example, we would say that where y final is equal to 0, y final, right? We could say that the total distance, right, or the displacement, is vi initial times time plus 1/2 at squared. And we know that we can replace total distance, or the displacement, total displacement, being the final displacement minus the initial displacement. We know that we can do this. Final displacement minus initial displacement, right? And then we know that we can equate this to, you know, we can break this down, vyit plus 1/2 gt squared, where a is just gt. And once we start solving for things, we can say that y final is equal to y initial plus v initial on the y-axis times time plus 1/2 at squared. We've used this in programming. We know that y final would be 0. That's the idea behind it. So this is the first way of doing it. Okay, the first way is, how do we know the time it takes? If y final is 0, now we have a quadratic equation in the form of ax squared plus bx plus c, where x is the total time. We know that y final is 0 because it's going to kind of hit the ground. And once we know that, we can put that into this kind of equation, where we can see that where the final term, h, and this would be y initial, some value h, plus v sine theta t. V sine theta t, because why? Because we can break this velocity value, number of velocity and sine are related. So you can take these two things and say that vyi is v sine theta, right? V sine theta t plus 1/2 gt squared. And then we can use the quadratic formula to help us solve for t. Now you're going to get two values. There's going to be a positive value and there's going to be a negative value. Obviously, we can't use the negative value, as we said earlier, because the only people that can have negative time values are time travelers, which don't exist in our world. At least not now. Sorry, Dr. Wu. Alright, but then if you look at this, how do we plug this stuff in? Well, we know that this term here would be the a term. So we would take anything that has a in it, we would replace with 1/2 g, right? 1/2 g, that would be a and a. And here you can see that this would be the b term, so anything v sine theta, that would be anywhere where b is. Take this b term, put it in there. And then this would be the c term, right? So we take the c term, plug it in right here. It's the only place that it can be put. And then once we've taken all those things, we solve this little equation, this little formula, and then we've got time, and whatever that is. Okay, so that's one way of doing it. Second way to do it is to kind of break it up like we saw. We could break it up between A to B, which is right here, and then B to C. Could do it that way too. So we know that the time between A and B, if we're going to look at the total time it takes, is v sine theta over g. So time from A to B, v sine theta over g. This is where the total on the y-axis, as an example, final y is equal to 0, and this would be your initial y over gravity. That's what it would be. Once we know that from A to B, we need to find the height between A and B. So that would be this height. And again, it would use the same equation, just like we would normally, as v squared sine theta squared over 2g. That's the height, capital H. We also know that y, total y, is 1/2 at squared. That's the total y, the total distance. So we can start saying that the total height is little h, which is the height of the hill, plus big H, which is the height of the parabolic arc coming off the top of the motion. Taking that information, where y max is equal to h plus h, taking all this plus all this, that's y max, or the apex. We can plug in the formula from B to C, where we can say B to C is 2 times y max over g. And once we've done this, we just take different piece parts. We take the total time from A to C, then would be the total time from A to B plus the total time from B to C. So this time plus this time. And those are the equations that are useful for us in this third scenario. To find the range, again, we do the exact same thing. Vx times time, where Vx is equal to V cos theta, where cos is related to x, right? And we can also find the final velocity. We can take the initial velocity times sine theta plus gt, and then we can say that we can split things off once you find the final velocity, and then you can find out what the component velocities are. If you want to find the angle, knowing what the component velocities are, you can take Vy over Vx, take the arc tangent of that, and you can figure out the original kicking angle. Okay, so those are all the things that we can use that are in our toolbox. And again, like it says here, make sure when you plug in values for Vx and Vy, the values are positive if you can, and that you'd have to adjust your coordinate frame for you to do that. One thing to note is that, like it says here, the vertical velocity at the top of the arc is always 0, because we talked about this as one force canceling the other force out. Force of gravity, or the acceleration due to gravity, is pulling down. Velocity, from the kicking angle is going up. It's going to, kind of point in time where the acceleration that's pulling down, the velocity is pulling up, it kind of equalizes so that there's no velocity whatsoever, and that's what's happening here. And they can describe this idea of the initial velocity and what happens to it when we analyze projectile motion. I'm just going to skip some of this stuff until we get to some other stuff here. So here we have the maximum height of the projectile that can be found in terms of the initial velocity vector. So we can see that the initial velocity vector squared, sine squared, times theta, initial whatever this is, over 2g. This is the total height of the object in symmetrical motion. Total range then would be the same thing. The range would be equal to vi squared plus sine 2 theta over g, based on the velocity this time. This one was based on the velocity. Notice the same. So same equation, isn't it? The only difference is that height is 2 times gravity, where range, if you will, how far it goes, is only 1 times gravity by 2 times the angle. The other thing that we want to also look at is different angles produce different ranges. And it looks to me that the most efficient range that you're going to get out of your projectile based on the same exact speed is at 45-degree angle, right? So you can see that that's going to happen there. But the rest, notice that 75 here, an angle of 75 from the horizontal is equal to 30 or 15 on the horizontal. It'll kind of land in the exact same spot. And again, just like we said earlier when it came to our lecture a few weeks ago, this will take a lot longer than this. Both will actually hit the exact same spot. And same thing goes with, this angle here, which is 60, and then this angle here, that is 30. Notice that both the complementary angles add up to 90 degrees. Okay, that's what they must do in order for this to work. Alright, and the reason why 45, theta at 45 is the maximum range, angle for the maximum range, is because when you take 45 multiplied by 2, you get 90. That's the perfect kind of angle for the maximum range that your projectile is going to go based on Earth's gravity. We don't always do that. We don't fire up 45-degree angle. Usually we fire ahead, and for most projectiles you're going to say, well, wait a minute, if we want to get 45-degree angle, we want to have a long shot, then that's the best way to do it. But if I'm kind of firing my my projectile, as an example, I'm pointing forward at a target in front of me, and a velocity, a muzzle velocity that's fast enough, like a gun, chances are that projectile is not going to hit the ground before it hits my target. It's going to hit the target first. So that's why people don't aim necessarily at the sky when they fire at someone else. When it comes to conceptualizing, again, from a problem-solving perspective, we always want to think about how we can break the problem down into different steps. Conceptualize, categorize, analyze, and finally finalize. Right? And it talks about this on the slides. It talks about how to do that. I'm not going to cover that here, but we've already covered this one time. This whole kind of idea of how to break things out. But the first thing you do, like it says here, is mental representation or an image of what's happening is very, very important. Let's try and solve this one. So we've given some information. Given that we have, a total height 45 meters, and we have this man. He is throwing an object off of the top of a tower at what looks like 20 meters per second at an angle of 30 degrees. So the question would be, how long does it take for the object to hit the ground? What's the range of the object away from the tower base? Right? So some things that we know. What's the total height of the displacement? What's the highest height that this object can get to based off of our equations? What can we do there? So again, if I was going to go, I would start planning some of this motion. So let's break down into vertical and horizontal components. Right? So that's what you want to do. You want to break these components out a little bit. Right? So what do we know from a horizontal? What do we know from a vertical? What can we plug in for us to figure things out? Now, going back up to the equations, we're going to pull some of this piece of information that we know back in. One thing we know is when I want to find the total range of a projectile, just go back up and all the way to the top. Remember, we tried to solve this equation, and we're going to try and do it the fast way. There's actually two ways of doing this thing, right? So the fast way tells us there's a couple of pieces of information we can use, right? So we know that this equation, number one, is one we want to use. So again, displacement, total displacement across the y-axis, and again, this is not written very well, but total displacement of the y-axis is Vyit plus 1/2 at squared. We want to take this equation on the y-axis first to figure out what's the total time it's going to take us to get there. And when we do that, we want to break it out into this form, which actually looks like this at the end. Take this is going to calculate the total time it takes for the object to hit the ground based on its initial trajectory or initial angle, kicking angle. I'm going to take this formula, and I'm going to go back down to a little example here, which is way down here, and plug that in. There's not the way to do it. How about that? Let's try that again. So I'm going to take this angle, I'm going to plug this into an equation further down by inserting a text box, and we're going to put that in there. I'm also going to insert a formula, and you can see that the formula is going to look something like this. So that is my initial formula. There we go. And this is what we know. Now let's fill in the blanks of what we know. So we know this is 45 meters. We know that. That's the total height. Right? Now again, think about this. Would we put the total height, are we going to put the x and y coordinates there or down here? Well, here you can see that the x and y coordinates are at the top of the motion, not at the bottom of the motion. So up here. In this case, it's going to travel a negative 45 meters velocity downwards below the horizontal, which is up here. So, again, if this h was a negative 45, that would have been over here. But we're putting it on this side, so this would just be 45. Right? We're going to put that in brackets. So these are the things we know. What are the things we know? We also know the initial velocity, which is 20 meters per second. So again, we're going to take the initial velocity and kind of sub that in. 20. What else do we know? We know the angle. The kicking angle is 30 degrees. Let's put that in there. So, and sine of 30 degrees. We know that. We also know GT. GT is going to be a negative number, right? Now, caution here when it comes to it. We have to be careful of what we use, but if we use the negative over here to bring this over here, then we must use a negative over here, which works out to be a negative 4.9. Okay, so that is our initial equation. I'm just going to move them around so we can see what those are on the vertical. So I want to solve for t, but now we've got this quadratic equation here. Let's do a little bit of simplification. So I'll simplify this term and this term a little bit before we move on, so we can make it a little easier on ourselves. So this term, 20 sine 30. So again, we can go back here. 30, right? Sine times 20 is 10. So this would be, this here, this term would boil down to 10t. So 10t. And again, this is 1/2. If I can put the, I already calculated it, negative 9.8. 1/2 of negative 9.8 is negative 4.9. So we would take this term out, and we'd have something that looks like this. Now I'm leaving it in this form. I could simplify and say 45 plus 10t minus 4.9 t squared, but really what we want to think about is that I've left it in brackets. We can simply see what we're going to use next, which is going to be the quadratic formula, which we're going to bring in right now. So make sure I got the right formula in here. And I don't want you to suffer with the other method. So this is the one I want. I want this formula right here. So I'm going to copy this one. Again, I'm going to go down to what we were working on right here. I'm going to plop that in up here just to give us a little bit more room. So again, we want to solve for t here. That's what we want to do. And we're continuing with what we're doing down there. And what I want to do is I want to plug in all the values that I know. So again, you can see that this would be C. So again, I would kind of do one of these. 45. This would be A, meaning A would be negative 4.9. This is good. Negative 4.9. Why would this be good? Because you can see that a negative times a negative here would be a positive at the end. B squared, B being this number right here is 10. So again, this should be like 10 squared, right? That's B. Sine 30.5 times, this would be B. And then finally, this would be 10 minus 10. Let's do that. So minus 10 plus or minus square root of 10 squared minus 4ac over 2a, right? And then 2a, of course, would be 2 times negative 4.9. We want a negative number on the top. Otherwise, this negative 4.9 is going to bury us into time travel, which we don't want. So this would be like a negative 9.8 when we figure it out. Are you with me? because this is where we have to start, my friends. Let's do some simplification. So again, I'm going to bring this up, and I'm just going to make it just for us, for our purposes, I'm going to just drop that size just so we can see it on the same screen. There we go. So we want to simplify this. Let's make sure we have everything in place. A, negative 4.9, right? That's what it would have been. C being 45. B being 10 squared, which is just equal to 100. So let's do that. So again, it's negative 10 plus 100. By the way, what happens if we make a mistake? How do we know it? So we'll know the numbers are wrong, rough. And then we have this situation. So negative times a negative, this will be a positive number. Whatever this works out to be, it'll be a positive number, some positive number, right? And then here, this would also be a positive number because now we've eliminated the negative. Negative times a negative, they're gone, becomes positive. And let's 4 times 4.9 times 45. Okay, so 4 times 4.9 times 45 is equal to 882. So this whole part here, if we calculated it correctly, is 882. We may not have. (882) over negative 9.8. And now let's just put this over here. So again, we continue to simplify for time. And we can see that negative 10, 100 plus 982. So again, if I was to look at this, plus 100, 982, and then take the square root of that, we're going to get 31.3369. 31.3369. I'll take that number. So that is equivalent to all of this. I'm just taking the square root right now. 69. So minus 10 plus a positive 31.3369 would be a positive over a negative, which would be a negative number. So that means we don't care about the positive value, we care about the negative value, which would add up to be a negative over a negative, which would turn out to be positive time. So then t would be equal to negative 10 or minus 10 minus 31.3369. So this is this plus 10, right? Plus or minus, so negative 41.3369, right? Over negative 9.8. I'll do it in one step, right? So divided by 9.8, negative over a negative is a positive, 4.2180. And if we round up this to 9, 9 to 5, 5 to 1, we can say that this is 4.2181 seconds. Does that make sense? And is this the right value? Did we mess up? Did we mess up somehow? Again, let's cross-check our work. So again, 20 meters per second, 30 degrees. 20 meters per second, that's the initial velocity. 30 degrees, 0.5 times 20 is 10. Again, let's check that, make sure it's right. So again, 30 sine 0.5 times 20, that's equal to 10. We did that correctly, right? 0.5 times 20 is equal to 10. This is the big one. And then once we know that this is 10, everything else seems to be in order. So time then, the total time it takes for this object to hit the ground from the top of the cliff all the way down is this. Okay, what's the total range? How far does the object travel away from the cliff? Well, that's pretty simple. Once we know the time it takes, then going back to our equations, we want to find the range, keeping everything positive. We want to use this, right? Range is equal to v cos theta t. Right? We know time means you can plug in this. So let's do that. So take this range and go back to our little equation, which is over here. Plug that back in. So there's our total range. How far did the object travel, is what we're saying. Away from the base of the tower. How far did it travel? Well, if we plug in the values that we know the initial velocity, right, that was given to us at 20 meters per second. 20. Now it's cos theta t. We know that cos of 30 degrees, we know that there's a different value. That's what we're going to plug in. And we also know, actually, let me just do it one more time, guys, just so that you have the entire thing here. You can probably figure this out, but I want to make sure that it's all recorded nicely for you. Again, this is 20. This is cos of 30. And this t is this t value right here. Right? So, how long does it take before it hits the ground? 4.2181 seconds. That is what we need to figure out here. So let's try and figure this out. So again, we'll start with cos. So 30 cos is 0.866, right? And just like it says here, we're going to take this 0.866 multiplied by 20, multiplied by 20. So you can see that there's more energy across the x-axis than there is in the y-axis in this case, right? So this is the energy across the x-axis. And then multiply that by the time. .2181 again equals to 73.0596. 73.0596, let's say. Meters. Does that make sense? So again, with a muzzle velocity of 20 meters per second, we're at a 30 degree angle from the horizontal. This thing drops like a stone until it hits the ground. It takes 4 seconds for this to happen. And it's going to drop, as an example, to a depth or to a range of 73 meters away from the tower. Notice that it's almost like double the height of the tower is going to go. This is how far it's going to go. It's going to be way over here. Alright, so that is the first part of our lesson when it comes to simple kinematics. Now we didn't cover motion number 2. That's simple. That is literally, the total distance. If I want to find the total distance or describe the curve, it's, the final position is equal to the initial position plus the initial velocity times time plus 1/2 at squared, but we take the initial velocity and componentize it to both the x and the y axis. Okay. So if I wanted to find that out, I could just take, the total time it takes for the object to fall, right, to get, to go all the way to the other side, as an example. Solve for t, and then from there we know how long it takes before the object stops moving on the x in the horizontal direction. Alright, so that is the first part. Then we get into this one, we get into something called uniform circular motion. It's a totally different topic, but I want to cover it here anyway, so we can cover PowerPoint number 5, right? So here what we have is a changing velocity in a uniform circular motion. Uniform means that it's going to continue like almost exactly symmetrically or exactly the same way. Now there's 2 types of circular motion that we're going to talk about eventually. One of the types is horizontal circular motion, where it's going this way, right? And we can, when I'm imagining that I'm holding some kind of cable in my hand as I'm spinning an object around, let's say my head, right? And there's horizontal motion that kind of goes this way, a kind of up and down motion like this, where I kind of take, the center of the cable and I'm kind of rotating in a direction. Now this is asymmetrical because it speeds up and slows down. As the object comes up in the motion, it starts slowing down, and as the object comes down in the motion, it starts accelerating. And we're going to see that, maybe not this PowerPoint, but another one. But here we can break this down to something called centripetal force or centripetal acceleration. What's happening is it's always perpendicular to the path of the motion, and it goes inward. So when we describe a path, this motion path, the acceleration actually goes towards the center or of the radius, whatever, or the radius of the motion. So even though you can see here that the initial, here's the initial distance or displacement, and then here's the final, and then we can see the change in the displacement here from here to here. We can see that, and it describes motion and everything else, just like we saw before. The actual acceleration goes inward towards the center of the motion, okay, and that is called centripetal acceleration, right? So towards the middle, and we can describe it with a formula. Centripetal acceleration is equal to velocity squared over the radius, whatever the radius is, again directed towards the center. If we want to find the period, right, how long it takes for this motion to happen for one revolution, we can simply say that 2 pi r, which is the circumference of the circle, over the velocity is the total period total time in seconds it takes for an object to travel around, the projectile to travel around a center, an orbit, or orbit around a center as an example. We also can say that the magnitude of the velocity could also be changing, so we can have something called tangential acceleration. Tangential acceleration happens when we have this motion, like we said, a motion this way. If we want to find kind of acceleration this way, or centripetal acceleration towards the center, you can kind of do this, but when we want to find a tangential acceleration, acceleration tangent to the curve, if you will, right? Then it would go away the other way. We're going to show that in a second. There's one more type of acceleration. So there's 3 types: centripetal, tangential, so tangent to the motion, and radial, right, which changes direction. So what it works out to be is that, again, acceleration, tangential acceleration, is the absolute value of the change in velocity over the change in time. That's tangential acceleration. That is tangent to the curve. Instantaneous acceleration at that particular moment. That's what that is. Radial acceleration, on the other hand, is, we can say that it is the negative centripetal acceleration. That's what that is. That's like saying, so centripetal acceleration goes into the middle of the motion, and radial acceleration goes outwards from the center of the motion. You can see that they are opposites. And if we take acceleration, we know that acceleration is equal to v squared over r, right? That's centripetal acceleration. And we have a negative number. We can say that the radial acceleration is a negative v squared over r. Sometimes we also want to find the total acceleration. Total acceleration. So both radial acceleration and the tangential acceleration, so radial being outward plus the tangential acceleration being tangent to the curve, we can find the total acceleration. And we can find that just by using something like, that's very similar to, it looks very similar to Pythagorean theorem, because we're making triangles as we're going around the curve, and we want to find the total acceleration as we accelerate around the curve. One thing we mentioned in class, but we're not going to cover in this course, is any kind of relative reference frame. So we're not going to be talking about relativity. That's kind of out of scope. We're also not going to be talking too much about this idea of, a frame of reference. We're not going to be talking about that at all, right? But one thing to note is that there is such a thing. Frame of reference is looking at, we kind of look at an object. We're an observer outside the frame, as an example. And I'm going to give you this idea over here. So here you can see a woman. She's standing outside of these people moving on a slide walk, if you will, right? She is observing these people moving, and to her, from an observer's perspective, they're moving quite fast. However, when you're in the frame, so this is the outside of the frame of reference, right? But however, when you're inside the frame of reference, almost think about this as a container that you're inside of. When you're inside the frame of reference, you don't feel the acceleration. For you, the local acceleration for you appears to be 0. Why? Your whole frame is changing. And a good example of this that we talked about in class was our frame of reference being on the Earth. We don't feel the motion of the Earth, the acceleration or the radial acceleration, or the centripetal acceleration of the Earth that as it's orbiting around the sun. We don't feel that. We also don't feel the Earth orbiting around itself, spinning around itself. We don't feel those motions. We are inside of the reference frame. We also don't feel the sun itself moving along the axis of rotation for the galaxy, the Milky Way galaxy. Nor do we feel the Milky Way galaxy's rotation as it moves around some kind of, universal center. We don't know that. Everything is moving in space, including our galaxy, but we don't feel any of that motion because we're inside of the frame of reference. And we talked about also during class that this could be a problem when it comes to things like teleportation. If you're a sci-fi fan, you always think about like transport them down to the surface, Captain, and Star Trek. And of course that's not going to happen so easily because you're moving. The surface is moving. Things are changing, especially if you're orbiting the Earth. You've got to compensate for this kind of thing. And that's one thing. Teleportation from, space to surface, that's one thing. But teleportation from surface to surface, oh, that's something else. At least in orbit, you're in geospatial orbit. You're moving along with the Earth, almost like you're inside the reference frame. So therefore, if there was such a thing as teleportation, instead of beaming down energy, you can actually see the place where you're beaming. But what about if I want to, teleport from, let's say where I am right now, which is the university, all the way to home? Well, that would be a totally different scenario if I could somehow do that. Why? Because even though I'm in the reference frame, by the time I teleport, there's going to be a shift in the reference frame. The Earth is moving constantly. And where I'm targeting today is not where the Earth is, or this moment is not where the Earth is going to be in a moment from now. Let's say another second or so, however long it takes for me to teleport, right? So then, therefore, I'd have to adjust for where the Earth is going to be, right? Because our Earth is moving all the time. And furthermore, how far away is it going to be? From a galactic perspective, there's also other motion happening. That point in space, that global position that we're pointing at, that's local to the Earth, is also going to shift. We have to compensate for all the the motions of the universe, if you want to be totally accurate. But we're not in science fiction, and we're not in space, and we're not beaming anybody anywhere. But that's kind of the extent of what we're going to be talking about in terms of frame of reference. And they have some notations and everything else in terms of transformations that you can make. But we're not going to really care about that because it has nothing to do with us from a game dev perspective. Alright, so sometimes what ends up happening is we had some difficult questions on our test, and I was going to cover some of this stuff. I'm not going to cover this now because we'll cover this again back in class. Let's get back to this. Projectile motion example. So here's a few of them, and again, for the people who are going to do their homework, I'm going to open it up this week. Between pages 73 to 77 on your PowerPoint are going to be due. But let's try and think about the first one before we stop this recording. Let's try and think of this. A water balloon is thrown horizontally, right, with a speed of, and it says V naught. The initial speed is 8.3 meters per second. Okay, cool. From the roof of a building of a height of 23 meters. How far does the balloon travel horizontally before striking the ground? Okay, so the first thing you should ask yourself is, what type of motion is this? Is this type 1 motion, type 2 motion, or type 3 motion? And if you look back up to the motions, so here's type 1 motion. It looks like this, right? We weren't given an angle, right? Remember, we have to think about all the information we've been given. We've been given a height, which we normally have. We've been given a velocity, right, on the x-axis. And that's it, right? So height and velocity, we know the acceleration because of the gravity, so we can actually literally plug in the equations that we know. Go back to the actual stuff here. For motion, type 1 motion, basically, which is something kind of coming off. It's almost exactly the same as what we saw earlier. Let's go to the next one. An object is fired from the ground at 100 meters per second at an angle of 30 degrees. Okay, that is the kicking angle. So I've got an angle, 100 meters per second. I'm firing it off the ground at 30 degrees. That's type 2 motion. And then calculate the horizontal and vertical components and so on. We can do that. Third one is Mary throws a ball in the x direction with an initial velocity of 10 meters per second. Time elapsed during the motion is 5 seconds. Calculate the height that the object is thrown and the Vy component of the velocity after it hits the ground. That's interesting. So we've been given some information. It's weird too. We've been given some extra information we don't know what to do with. So Mary throws the ball to the x direction. That means across the horizontal with an initial velocity of 10 meters per second. We know the x direction. Time elapsed during the motion is 5 seconds. What is the, if I'm going to break this down into horizontal and vertical, what is the vertical speed that we're sending the motion? Well, obviously the vertical speed is 0, right? So we have a vertical speed of 0, but the horizontal speed is 10 meters per second, and we've been given a total time, 5 seconds for the motion. During the motion, 5 seconds. Calculate the height that the object is thrown in the Vy direction if it takes 5 seconds for it to come down. That's how long it takes for the motion to stop. We don't know what Vy is, but we know it takes 5 seconds for it to stop. Again, this is type 2 motion, but we have some of the information, not all of it, and we don't have the angle. We can figure this out taking the arc tangent of the motion based on some of the stuff we've been talking about before. So let's figure this out. The next one is Adam kicks the ball, and the ball has a projectile motion with an angle of 60 degrees to the horizontal, so some kind of upward motion. Initial velocity is 10 meters per second. This is type 2 motion. Find the maximum height it can reach. So we're looking for the height. And the last one is, given an object on a cliff, gets fired, and given the initial velocity of 10 meters per second, the angle of 30 degrees, that's type 3 motion. So all these three things, an opportunity for you guys to practice this motion, these projectile motions, so that it helps you with the midterm exam, which is going to happen in week 10. Again, right now we're sitting at week 8. Week 7 we did our, we kind of talked about the programming. Week 8, right now we're kind of in midterm break. Week 9 we come back. Week 10 we're going to have our test. This is good practice for week 10. Again, I'll open up the Dropbox this week so you can have this done. So that's it for me for this PowerPoint. I've got one more to do, and then it has to do with Newtonian physics, which we're going to be talking about forces and all that kind of stuff coming up. I'm probably going to do that tomorrow if I can, right? So let's get that done. But that's the next part of the motion we want to talk about. So that's it for me. I will see you in the next video.